Okay.
Particularly the PMU phase angle difference. N value is given as 60.
Just
Can you
wait. Just a minute. Okay.
keep 10 assignment?
Yes.
Pick 10 assignment, question number
Second or third?
third one. Angle between two successive PMUs, non-recursive approach.
Yes.
N equal to 60, so it is 360 by 60. That means 6 degrees is the answer, but it is not there. Maybe N value may be 50. So that is why they have given a 7.2 as the answer.
N is equals to 60. Yes, it should be 6.
Yeah, 6, but the answer is not there. The option is not there. 60 degrees, the option is not there. That is one thing. And then the immediate question number 4. Find the inverse Fourier transform. That is 9 plus 5 into j omega by the j omega square.
Yes, that is j omega square, correct.
Square. And
that is j omega square.
Next one is which of the following? Sixth question, sir.
Sixth. Yes.
Question. A sinusoidal signal with constant amplitude, frequency, and phase angle of the non-recursive phasal estimation technique provides a rotating phasor. The answer is given as a recursive phasor estimation technique provides rotating phasor.
Second, recursive phasor estimation requires fewer computation. That is correct.
That also correct. Recursive phasor estimation technique requires a fewer computation. That one, because this is multiple answers, right? So the second one and fourth one are correct.
Yes.
But it is given as second and 1 and 2. 1 and 2. The answers given is 1 and 2. Which is, I think, wrong, but it is given as answer.
Yes, that is correct. Because the recursive, non-recursive,
non-recursive, there will be phase angle.
Yes, the angle changes.
Yeah.
From minus 180 to 180, it will change.
Yes.
Again, continuously it will be rotating. That is correct. That is also there in the figure which we have seen in the session.
Yeah. Shall we start, sir?
Any other doubts in that?
No, not doubt, but the answers, there are some discrepancies in the answers. That is what I want to. Rest is okay.
That will be changed, I think. Yeah, so whatever you have pointed out, that is correct. Do you have, okay, let us start.
Okay.
Share the screen. Yeah. I hope it's visible.
Yes, sir. Yes.
So welcome for today's live session, the week 11 live session for economic operations and control of our system and NPTEL course. So today we will, yeah, tomorrow is the last date for submitting assignment 11. So are you done with the assignment 11?
Yeah, yeah. But there are certain problems now. We will discuss on that so that.
Are you able to do all the questions?
Yeah, majority of the problems.
Okay. Yeah, we'll take some, I think similar problems we will take up today and discuss in the end. And the assignment 12 has to be submitted on October 16th. Tomorrow is the, so October,
Ninth.
next week is the
Yeah,
last
yeah.
week. And after that, this October 16th, maybe that 16th and 19th. October 19th, we will be having one extra session.
Okay.
That session we will take problems for the entire course
Okay.
from week 1 to week 12. It will be kind of revision. So whatever doubts you have for all the weeks, you can ask. That will be on Saturday, I think from 3 to 5. The timing as well as the link will be posted in the announcement.
So why don't you have it now
Which
on the
one?
same name? It's 6 to 8.
6 to 8 Saturday.
Yeah, yeah. Because Saturday is a working day for us.
Okay, but actually I have already given that and the timing from 3 to 5.
Because we will be in the we are in the journey, traveling from college to our place at the time.
I think
It's
now it will be difficult to change.
okay.
Okay. If you have any, you can see the recording, and
Yeah, yeah, yeah.
if you still have any doubt, you can mail me.
Okay, okay. Can you give your mail, sir?
Yes, sure. Um, I'm just typing it in the chat box.
Yeah, yeah.
Yeah, it's available in the chat box.
Yeah. I think that's the number. Okay.
Yeah. So these are the topics which were discussed in this week 10. I forgot to change this title. This should be week 11. Correct it now itself. So this week was about this control of generation. This we have already discussed in week 1, right? Week 1, a small introduction was given.
Yes.
Quickly, all these things were discussed in week 1. Already this was discussed, control of generation. Given this energy storage, some basic classification of energy storage was also provided in week 1. As this was not discussed in week 1, short-term load forecasting. But pumped storage was discussed. I think gravity storage was not discussed. It was just only, I think, name was given. So this control of generation is same thing which we have already discussed. All the models and everything is same. Again, it was just discussed in a little bit detail. We'll see questions for this part. We had discussed in that hydrothermal scheduling. That lambda gamma iteration, right? Do you remember?
Yes, sir. Yes, sir.
So lambda is for, can you tell what is the lambda is corresponding to which? So is when we say we solve the economic dispatch using lambda iteration method. What is this lambda?
Lambda incremental fuel cost.
Incremental
Fuel cost.
That is the cost characteristics.
Yeah.
This lambda is for the optimal solution is that the lambda will be equal to IC,
Okay.
the incremental cost. But what is lambda?
Change.
This is the solution of the optimization
Okay.
problem, and because the cost characteristics is AP square plus BP plus C, right? This was the cost characteristic. And this IC, that means it is the differentiation, the incremental cost characteristics will be 2AP plus VP. When we say the solution of economic dispatch is that this is incremental cost, and at the optimal point, this is equals to lambda. So if we have two generators, then it will be, this is P1, 2A1, P1, B1 is equals to 2A2, P2 plus P2, P2. And we have one more equation that P1 plus P2 is equals to load. So when we solve all these equation, we get these variable, this P1, yes, P2 and lambda. We have three variables and three equation. We are able to solve it, right?
Yes.
So this is the solution of, this is the condition or the at optimal point, this will happen. But what is lambda? That question is, what is lambda? Our problem was, if we take economic dispatch, then it is minimize summation of, it is minimize the operational cost, right? Subject to right. This is the problem. Simple.
Yes.
Neglecting the losses. Now, can you recall what is lambda in this problem with respect to this problem? Where does the lambda features? From where does the lambda comes up?
Yeah. So coefficient which is Lagrangian multi.
Yes, correct. So if we solve, if we write, what is the first step? We write the Lagrangian function, right?
Yes.
So this will, it's a function of
So
the
cost
variables,
plus
optimization variables, as
yeah,
well as this Lagrange multiplier.
like a multiplier.
And this Lagrange multiplier is the dual variable for the equality constraint.
Yeah,
This is the equality constraint, and this is the these are the
inequality.
inequality constraints. So we have here, let's say if we have n generators, then these are two n inequality constraints.
Yeah. One is for real power,
One,
and the one is a reactive power.
no, one for upper bound and one for lower bound. Here, we are
Sorry.
only
Reactive power is not considered. Okay.
yeah.
The only real power.
Yes, so we have only real power, but there are two bounds. One is upper bound and one is a lower bound.
Or bond. Yes.
So that's why we have n lower bound constraints and n upper bound inequality constraints. So overall, we have in totality we have two n inequality constraints and one equality constraint, which is this. So corresponding to each inequality constraint, also we have multipliers, dual variables. So maybe mu I bar generally this upper bar, lower bar we use for, and if lambda, gamma, or mu we use, mu generally we use for inequality constraint. So upper bar indicates the multiplier corresponding to the dual variable corresponding to the this upper bound constraint, and this lower bar corresponding to the lower bound
Yes.
constraint. So these are the dual variable corresponding to the inequality constraints, and this lambda is the dual variable corresponding to the equality constraint, and this is also the Lagrange multiplier. And using this, we are actually what we are doing here, we are converting this problem into an unconstrained optimization problem. The Lagrange multiplier is a method. Lagrange function is a method where we are converting. This is a constrained optimization problem, correct?
Yes.
Because we want to achieve this objective with respect to these 2n plus 1 constraints. But Lagrange has given us a way where we can convert this, we can move these constraints, 2n plus equality and inequality constraints, into the objective function using these dual variables. And they are also called as Lagrange multipliers. So if we remove or let us only consider this equality constraint, if we let us forget about the inequality constraint, then it becomes simply our objective plus actual original
Lambda
objective function for lambda times.
equality constraint.
Yes, so summation of pi minus pl. So now there are no constraints. No constraint is there. Constraint has been already moved into the objective function. Now this becomes a simple unconstrained optimization problem. Now minimize this Lagrangian function with respect to pi and lambda. So now there are no constraints. If you want to consider the inequality constraints also, then we can include that also. Then here it will be summation mu I bar, mu I lower bar. So pi minus pi lower bar minus pi plus summation of mu I upper bar into pi minus pi upper bar. So this will be the overall Lagrangian function considering equality and inequality constraints. Now for when inequality constraints are also there, we have to consider, we have to see the KKT condition. We have to satisfy this KKT condition. So all this we have already seen. Just it was a. I just wanted to remind you about this lambda gamma iteration. So because we forget, this is a very important point. Whenever we go these, especially these equality constraints, the multiplier, the dual variable associated with these equality constraints are very important. And especially when we consider the network also, we have discussed this LMP, right? Lagrange multiplier.
Yes.
Sorry, locational marginal pricing. Remember?
Yes, sir. Yes.
So in that case, here in this equality, that is also correspond. It's a dual variable corresponding to the equality constraint. But only thing is there here, in case of LMP, network is also present in this equation. If we consider the DCPF power flow, so what is the constraint, equality constraint in DCPF? What is the equation? We have solved numericals also on that.
Yeah, yeah. Mm.
How do we relate injection and this? If
Power
we have,
that is equal to the matrix B into angle theta.
yes, so simply if we take this line and it
Yeah.
has some reactance X and we have these, let's say this is
U12
bus
is
I.
theta 1 minus theta 2 by x, x12.
Yes, correct. So the power on this line, power flow on this line will be 1 by X delta 1 minus delta 2.
Delta 2.
So this is captured by this.
Yeah.
Now this same equality constant we can write this P is representing this summation of Pi minus PL. But here, because here we are not considering network, so we are aggregating the generation. Total load is equals to total demand. Summation of total generation is equals to total load. But when we have network, we have to do it node wise or bus wise. If we have a 3-bus system, let me add one page here. If we have a 3-bus system, and the problem, the economic dispatch problem without network is like this. We have only one bus, the entire generation is, this is summation of generation and this is total load. The equality constraint becomes this, and we have only one dual variable, right? Correct?
Right, right.
But how this will change here? What will be the change here? Now, how many equality constraint will be there?
At each node, you
Yes,
have to,
we'll be having a nodal power balance.
yeah.
Each node will be having one equality, one equation, one power balance equation.
Power
Right?
injected into a bus is equal to leaving the bus.
Yes. So these two
So
will be
P1
there.
is P12 plus P13.
Yes. Let's say this is P injection 1. This will be equal to. So this is one first constant. Similarly, we can write P injection 2 will be equals to minus P12 plus P13.
Two,
This will be equal to.
two,
Minus P12 plus P13.
P12 plus P13.
P12 let's say we can see this is the direction, and it will be minus
323. 32.
3 2. Similarly, P injection 3 is equals to
P31 plus P32.
P31 is coming, so it is minus P13. Yeah, P31 that we can
P31
say
plus
P3.
P32 because
Yes,
this is a
yes.
load.
No, we have to take only one assumption. If we had taken convention like this, then we have to take that convention only. Automatically, it will become negative or positive.
Oh yeah.
So we have to follow only one convention. So once the network is fixed, we have to assume one convention. Generally, we take the convention is to consider it from lower index to higher index. Okay. If bus it is M to N or I to J, because it is connected between 1 3, so generally we take it is the power flow is from the lower index to higher index, like 1 to 2, 1 to 3, and 2 to 3. So this is lower and this is higher numerically, right? So this is the general convention, but we can take another convention also just to have a uniform convention, because we have to code everything, right? So once the convention is considered, we have to stick to it. So here there is only one Lagrange multiplier. Here we have three, and they will also give us they will give us the location margin pricing. So if lambda, when will lambda 1 be equal to lambda 2 equals to lambda 3? Under which condition will this happen? These two are very related. You can answer this question by relating these two problems. These two are same. There is only one difference, and the answer is hidden in that difference or similarity, you can say itself. Can you recall? Anand, do you recall? What is the similarity between these two problems? These two problems. Yes. Are these two problems same?
Because this is a network and there are generators at some buses and there is some load at other bus. Um,
This we can easily go from this problem to this problem, right? Actual problem is this. And if we make an assumption here that all the generation
at the one
and
place.
all the load are on a single bus,
Okay.
then this problem 1 is converted to problem 2. This 3 constraint becomes 1 and we have only one lambda, right? This problem assumes that there is no network. In
But
one
there is a
sense,
network and there are certain losses here
here
in problem one.
in problem 1 there is no loss. Because there is no network, so there is no loss.
The problem one means the three bus system.
Sorry. Yeah, problem 2. No, let us assume there is no loss right now. Even in problem 1, no loss is there. We
Okay.
are
Only
neglecting the
resistance.
losses. Only
Okay.
power flow is there. Even if we consider that in this problem 1, although the generation and load is distributed, but if we make one assumption that the line capacity is unlimited,
Okay.
then it is same as this problem 2,
Yeah.
right?
Yeah.
Whatever generation is there, it can directly meet the load. There is no problem. There is no violation of any constraint.
Yeah.
It is same as this. Only thing is in problem 1 we will get an additional information that at each node how much is the generation.
Yeah.
Otherwise everything is same. So in this problem, if we if there is no congestion, there is no line limit is violated or hit, then these three LMPs will be same. So this will happen when there is no network congestion.
Okay.
And this will be equal to this lambda. These two problems will give you same LMP if there is no congestion. The moment there is a congestion, this will change.
Yeah.
Okay, is it clear?
Yes, sir. Yes, sir.
Yeah, so that is very important. You have to remember this always. Whenever we talk about this lambda and gamma, these are the dual variable corresponding to the equality constraint. So if lambda is the uh, dual variable or Lagrange multiplier for the power balance equality constraint, then what is this gamma? If this is for an equality constraint, this should also be for an equality constraint, right?
Hmm.
But which equality constraint is it? So what are the two equations? So the first one is power balance. We want to satisfy it. What is this? This is coming from the electrical, this power balance, load generation balance. This gamma is corresponding to which balance? What are we trying to balance here?
I think hydrothermal coordination. The
Yeah.
hydel.
So this is corresponding to total generation is equal to load. And this is corresponding to,
Hydro constraints
but what is that constraint?
related to inflow and
Yes. The total, that is water.
water well.
Whatever water inflow is there, inflow is equals to outflow.
Yes.
Please so remember these two always. So whenever you come across an operation problem, you have equality constraint. These their associated dual variables are of importance. Okay.
Okay.
This we discussed this one in the week 4. The same thing here. It was used here for pumped hydro storage also.
Yeah.
Then apart from this pumped hydro storage is a kind of, we had discussed in week 1 there are different types of energy storage. We have electrochemical. Can you give some example of electrochemical energy storage?
Chemicals. Um,
It's the most widely used energy storage.
Petrochemical means the batteries.
Yes, we have these battery energy storage, different types of batteries. We have these
Yeah.
redox, low batteries, lithium ion, lead acid,
Lithium-ion batteries.
metal ion, metal air.
Yeah.
All these different types of batteries are there. These are electrochemical. Then, so what is
Mechanical.
this? Yes,
Mechanical.
pumped hydro is a mechanical storage. And what about this gravity storage? Have you heard of this gravity storage?
Mm.
Okay, first, what are, apart from these two, is there any other
Mechanical energy storage is there.
any
Um,
other mechanical energy storage which we have
mechanic-
discussed in
flywheel we have discussed.
the flywheel, and one more we have discussed?
And then thermal energy storage we have discussed.
No, in mechanical we have discussed one more.
Uh, apart from flywheel, okay, storage energy storage. Okay.
This also we have discussed. Actually, this pumped hydro is a kind of gravity resistor, and it's large. And on smaller scale, we can have uh, there are many ways. One common way is to have a building. In that, we can have blocks. These are bricks made up of certain materials. And we can, while charging, the charging process is to rise these bricks to a higher platform. So height of this building is enough to increase the potential energy of this brick. So the charging process is to elevate this brick to a higher level, to height. So this is done using different cranes, or there are many mechanical robotic cranes are there. So they will do it within few seconds. And why again, when discharging is required, again it is lowered down. In that case, potential energy is converted into kinetic, and then it is converted into electrical. Okay.
Sir.
There is one more way where we have natural these we have hills, right? Hillocks or hills are there. In that you would have seen ropeways. Have you seen ropeways?
Yes, sir. Yes.
It's based upon that principle only, similar to ropeways. So we can have, so this is the bottom of the hill, and this is the top of the hill, and we have a weight, similar material, brick, something, a heavy material, a block, and this block, when charging, this block is moved from this bottom level to the top level. And then while discharging, again it is, we can directly release it from there. No energy is required in uh, releasing or releasing that brick from the top level. We can simply, but we need bricks. Yes, Anand, do you have any question?
Good evening, sir.
Yeah, good evening.
Sir, I have a question regarding the solution of week 10 assignment.
Which
Is it
question?
possible to question number 2 and question number 3, sir? Week 10.
Yes. What's your doubt?
Actually, in the solution of week 10 assignments, detailed solution is not provided. Only the correct answer has been provided. So can
Yes.
we get the detailed solution? How the values we are getting?
So that question is already, have you seen the week 10 live session recording or PPT?
Yes,
You
sir.
can, in that,
I have went through the PPTs, but by using those formula, whatever you have discussed, sir, we are not getting the correct result.
yeah, so that answer is not correct. So that answer, question 3 answer is given as 7.2, right?
Yes, sir. Yes, sir.
So,
And
but
I
that
think it
will
was
be
coming to 6.
that will be for 50 hertz. For
And
60 hertz, the angle will be 6 degrees.
Yes. it was coming 6. And so what about
Yes.
question number 2, sir?
So question number 2, what is
Always
the
zero.
angle? Yeah, it is 0 because we are considering
Recursive.
in question 2 it is like this, right?
Yeah, question 2 is recursive and non-recursive in question number 3.
So this is n plus 1, right? So
Yes.
in recursive we are relating these two samples, and their angle is same because they are already separated by 360 degrees. So if this is theta, then this is, so it is same, right?
So answer will be 0.
Yes, it is 0.
Okay. And in case of question number 3, it will be, I think, 6 degree, but answer was given
Yes,
7.2 degree.
answer will be 6 degrees.
And in question number 6, I think correct option will be C and D, but it is given as B and D.
No. B and D is question number 6, right? Question
Yes, sir.
number
Question number.
B, recursive requires pure computation. That is correct. B option is correct, and D option is correct. B and D are correct.
And what about question number B and D, sir?
Yes.
Actually,
What do you think? Means, according to what's the correct answer? So what do you think? Let me
I
just
have
let me just
1 second,
show
sir.
one figure.
Actually, the phasor will rotate in case of non-recursive system.
Yes.
But what is
So
the answer? Answer is given. It is rotating in case of recursive system.
yeah,
So
so that needs to be changed. That's the answer. The option D is correct, right?
yes, yes,
So B and D are correct.
yes, sir. B and D are correct.
Yes.
Okay, sir. Thank you.
Any other doubt?
No, sir.
Okay.
So shall we discuss some problems on control of generation?
Yes, yes, we will discuss.
Hello, sir.
Yes,
Sir, I have one doubt.
yes.
In governor frequency control, is it possible that one generating unit will operate in overload condition?
Overload means above its rated.
Yes. Is it possible that it will will it operate at above the rated power?
No, it cannot go beyond its rated install capacity.
Because in one of the question,
Yes,
while
yes, correct. Yes, that question is only, it's a numerical based question. Value is,
so
you may get a value which is quite large. Means there was one question in which I think it was asked what's the change in generation required to ensure a tie line flow or frequency to restore the frequency back to a particular value, and the value, the change required was much more. It was, I think, 2 or 10 times more than the installed capacity. So that is not possible.
so
Like if
theoretically
it
only
is,
it is possible.
yeah. So let's say if it is happening, even if it is required, such a change is required. That means the control which is implying that such a change is required, that control is not enough to ensure to achieve that, to restore that frequency or to restore that talent flow. We need to have another control mechanism for that.
Okay,
So
means
what
control
happens?
mechanism is not
Yeah,
proper.
yes, that control mechanism is not sufficient. When frequency drops, let's say sometimes when frequency drops to a very low value, right? If there is a sudden drop in generation or sudden increase in load, and let's say initial frequency was 50 hertz and then it goes to 40, let's say new steady state it achieves at 48 hertz at some after dynamics, after a transient, based upon the droop control, the primary control, it reaches 48 hertz. Okay, so this is a,
Okay.
it has achieved a new steady state. But
Actually, as per the question requirement, total load demand was not getting fulfilled without overloading the generator.
hmm, yeah, so
To
that
fulfill the
means
one
yes.
generator was need to be overloaded.
Hmm.
So,
We cannot overload the generator.
so shall I consider the maximum loading as per the rating of the generator and load the another generator
What
by
is
remaining?
the question? Where is that
That
question?
is assignment
11.
11, sir. Yes, yes.
Question number.
Assignment 11, question number, sir. That is question number 3.
What will be the value of PA by, it's the ratio of PA, PB.
Yes, ratio of PA/PV is required. So here
What are you
PA
getting?
is having more than 200 watt, 200 megawatt.
No, no. So whatever you are getting, just uh, use that value only.
Okay, sir.
Because when we are doing this, if we consider only droop, here we are not considering that limit on generation.
Yes. A limit on generation has
So
not been
these two
considered.
equations will not ensure that the generator will be at its limit. We are only
Oh,
having two equations. One is summation of generation is equals to load, and the other two equations are coming from the droop characteristics. But these are only three equality constraints. They do not ensure that the PA will be between 0 to 200 and PB will be between 0 to 400.
The data may be randomly given.
okay.
Yeah, it is because of the data.
Okay. Sir, in assignment 12, question number 1.
We have reached assignment 12. Yeah.
Yes,
Okay,
sir, I
let me
have.
see because I have not seen that. Let me open.
Yes.
If
Actually, line impedance
assignment
is given as, uh,
0.12
0.12
ohms
per
per
kilometer.
kilometer.
So is it the resistance or the combination of resistance and reactance?
Transformer impedance is 8%.
Because in question number 4, the same data and they have asked for the power loss. So power loss is only possible if there is a line resistance.
Distribution generally resistance value
Yeah, so
dominates. Maybe resistance is given because we generally don't neglect resistance in distribution. R by X value is
Yeah, sir.
large.
R by
It
X is
seems like it is
very.
resistance.
So if you take resistance, what is your value? What have we calculated the
Transformer,
value?
again, transformer, that is the reactance.
Yes.
Yeah, in case
So you
of
can
transformer, that will be purely reactance, but in case of line, uh, I think it will be proper to consider only resistance.
take resistance. You can take it as resistance.
Okay, sir. Okay, sir. Thank you.
Okay. Any other doubt?
No, sir. Thank you.
Okay. Okay. So I think slide is visible, right?
Yeah, yeah.
Where were we? We were discussing this, yes. Gravity.
Yes,
So
yes.
is it clear?
Yes, sir. So some numericals on control of generation.
Okay. I think all this, no need to go through this, right? We already
Yeah.
did. Sorry. This I could not remove it. Let me go to the end. Yes, this is the first question. In a two-area power system connected via a tie line, if load
Load
changes in area
changes
1,
in area 1.
then the new tie line power flow is influenced by the tie stiffness.
High stiffness, I think false it is.
Why?
High stiffness, the change in power flow depends on the change in frequency difference.
Only on frequency difference?
Uh,
If area, it is saying load changes in area 1, right?
yeah.
This is equals to at steady state. What will be the equation for second area?
Yeah.
This will be
Plus
delta
P2.
omega into d2.
D2.
And we also know that P mac 1 is equals to R1
R1 minus delta omega by R2.
So if we substitute here, then it will be minus is equals to delta omega d1 plus 1 by r1. And what is delta omega is equals to
Delta theta.
so we can substitute delta beta here. So it will be minus delta PL1 divided by
D1 plus D2 plus 1 by R1 plus 1 by R2.
and if we substitute it here, then beta is equals to minus delta PL1.
That is beta 2 by beta 1 plus beta 2.
Yes. So there is no stiffness term here. T is not here.
Yeah.
It depends on change in load. And
When you model tie line,
yes,
you'll get that equation delta theta is equal to 2 pi T1 2 by S into delta F1 minus delta F2. That is maybe a transient one, not steady state. You will
in
have that
steady
equation
state,
while modeling
in
the tie line.
yes, in steady state this will be 0.
Yeah. That is why the answer is false.
Yes. Second, a bar system has two generating units, unit A and B. Unit A has a capacity of 300. And unit B has a capacity of 200. It gain is 0.1 and for B it is 0.15. Demand is
Governor gain means is it R?
yeah, it is R.
Means you mean that is the regulation?
Yes. Frequency deviation is 0.02. Calculate the change in load required from unit A to restore the frequency to its nominal value. Yes. How will you do this?
Is it the change in load or change in generation? Because the frequency is deviated because of change in load. Now the generation has to change so that frequency come back to its normal. Am I right, sir?
So frequency is deviating.
Frequency is deviated because of change in load.
Yes. So how much change is required in generator A?
How much
That is the
change?
question.
Yeah, I think
It
it's
should
not
be delta
load.
P.
Okay.
This is delta P. So what will be the answer? How do we relate change in frequency to change in generation?
The system demand is 400 means uh, and the frequency duration is. So how can we understand this sentence, the statement? The system demand is currently 400 megawatt and the frequency deviation is 0.02 hertz.
Actually, this information is not needed here. Whatever may be the load, it is. If this was the load before
Okay.
frequency deviation, something the load changed, and the load has
We don't,
increased only. And
we don't know
frequency
the
has,
change in load.
yes, we don't know. So this information is irrelevant here, not required.
Okay. Okay.
The change in frequency is sufficient to know the change in generation from this.
Yeah. Delta F naught by R1 is delta F naught by R1 that gives the change in
Yes.
power.
So what is the answer?
0.02 by
This is one. This is one.
getting
And
0.02 by 0.1 means
but you have to see that this isn't per unit.
yeah, but the gain is also in per unit, right? Okay.
Yeah, but
Okay.
frequency,
Yeah.
this is 0.02 hertz. This is not in per unit.
Yeah. Yeah. 0.1
You have to convert it into per unit first.
into 60.
You are saying this?
0.2 by 60 means
Yes.
0.2 by 60. It is 2 by 0.0033.
Hmm.
So B is the answer.
Yes. Please correct.
Yes, there are two generators, and we need to specify whether which generator change you want to calculate, because delta
Yeah,
F
this
by
is
R2 is the change in the second generator.
this is for generator A
Yeah, yeah, of
first.
course.
Yeah, for similarly you can calculate for second also, right?
Second generator also.
How much are you getting? 0.02 divided by 60.15.
Point not 2 by 0.15 by 60. Point not 22. Point not 22.
Yes. Okay, this is correct. Answer B is correct.
Okay.
In this question, we have a direct formula.
Total time constant. I think between the total system time constant. Two times T tie 2. T tie.
Yes.
Okay. G1 10.
How much?
3.33 something. 3.3. 3.3 seconds.
Yes. This is the next question. An isolated 50 Hz synchronous generator is rated at 15 megawatt, which is the maximum continuous power limit of its prime mover. It is equipped with speed governor with 5% droop. Initially, generator is feeding 3 loads of 4 megawatt each at 50 Hz. One of the load is programmed to trip if the frequency falls down below 48. If an additional load of 3.5 megawatt is connected, then frequency will settle at. So this is part A. Second is, will the load trip? The programmable load.
Point 583 is the change, means minus 50. It is 49.417. 49.417. A is the answer.
Okay, how?
Using the regulation group.
Yes, using
The
group.
change, yeah, change in load is 3.5 megawatt.
Yes.
So delta F by the change in load is 3.5. That should be equal to the droop.
Delta F
Delta change
by
in frequency by change in load.
yeah, change in load is
That is the droop 0.05. That is to be converted to its frequency and power. So to be multiplied by 0.05 into 50 by 15 megawatt. So delta F is equal to 0.05 into 50 by 15 into 3.5. So that is the change. It's getting around 0.583 something. So frequency will be 50 minus 0.583, getting around 49.417.
correct.
So
Bus.
we need not consider all these things. The load is tripping or not, because the frequency drop
That
is only
is
0.583.
yes. So the load will trip only when the frequency goes below 48 hertz. But here the
48 hertz.
frequency, new frequency is 49.4. It is much above than the threshold.
Yeah.
The load need not worry.
Yeah.
It can remain connected and enjoy. Yes, you can directly calculate. Yeah, now this is the
This
second
one,
question.
okay, P1 plus P2. P1 plus P2 is given 400 megawatt.
Yes.
From that you will get F.
Yeah, this is very simple, right?
Yeah, yeah.
This is similar to the question which is there in the assignment also.
Yeah.
So, what is the answer? Calculate.
50.5 into 50 minus 50F plus 5150 minus 100F is equal to 400. 150F is equal to 50.5 into 50 plus 5150 minus 400 by 150 is 48.5.
Yes, correct. Okay. 48.5 is correct. Next question. The annual load duration curve of this is also a similar question. You have it in your assignment also.
Yeah, 60%. But average load by maximum load.
Yeah, so what is the
Since it
average
is straight
load?
line, it's 48 by 2 means 24 megawatt. Maximum load is 40, so 24 by 40, so 60%.
The average load is 48, 40 plus 8 by 2.
To 24.
Yeah, yeah, correct. So load factor is equals to average by peak.
Yeah.
Correct.
24 by 40.
Yeah, sorry, 40. Okay. Daniel, this is done. Yeah, I have one question. Let's say there is one pumped hydro storage.
Yeah.
And its installed capacity is, let's say 80 megawatts. Okay.
Okay.
And while charging, it takes 90 megawatt to charge to be able to deliver 80 megawatts. Okay.
Okay. Okay.
So that means it will take 90 megawatts of energy to fill the upper reservoir.
Yeah.
Okay.
But it is supplying only 80 megawatt.
Yes, but it will supply only 80 megawatts.
Okay.
This is while charging, it takes 90 megawatts. Its installed capacity is 80 megawatts. And it discharges
80 megawatts.
it discharges 80 megawatts, and in it charges in 5 hours.
Okay.
Okay. But it discharges at 80 megawatt in 4 hours. Yes. So what is the charging efficiency? What is the discharging efficiency? And what is the round trip efficiency? These are the three things you need to calculate.
Okay.
Can you calculate?
Round trip efficiency means is a product of
Yes, it is a product of.
charging
It
and
will be,
discharging,
yes. This is round trip efficiency.
which will be less than both. Any of these.
Yes, yes, it will be less than one because it is a product, right?
Yeah.
It's a 4 hour energy storage. So if
Yeah.
we, its rating will be 80 megawatt, 320 megawatt hour.
9 to 4. Yeah.
It's a 4 hour energy storage from hydro energy storage. Is it? It's easy question. It's inspired from a practical question. We are doing one project, so in that we had to model a pumped hydro storage, and from the utility we received the data in this way only, that actual values are different. I have modified the values. It is something similar, that it takes more energy for charging and then discharges for a lesser duration than it takes to charge. I just remembered that and fabricated it. Posed it as a question to you.
The charging, it is taking 5 hours. So charging megawatt hours is 90 into 5, so 450. Discharging it is 320 megawatt hours. So 320 by 40.
You are saying 320 by 450.
For discharging,
No, you are saying 320 by 450, right?
yeah.
So that is that will be the 320, which means 80 into 4. So this is the output.
Yeah.
And you're saying 90 by 50. This is the input.
Yeah.
So output by input, this will be overall efficiency.
Okay.
This was the input and this is the actual output. So it
Output.
is the
Yes.
overall efficiency. And how much
Yeah.
is it?
Round trip efficiency is 71% around.
Yeah. So this is overall efficiency, round trip efficiency.
Yeah.
But charging and discharging efficiencies will be different.
Very different. Yes.
This is easier to calculate.
Yeah.
For calculating these above 12 is that you need to think a little bit. It's not that difficult. Just try to think of it. See, what is the charging process?
Charging process, you need to pump the water back to the reservoir.
Yes. So
For that, you need.
how will you calculate efficiency in that case?
Yeah, the electrical components are not involved. One side there is some pumping means efficiency. It's a electromechanical mechanical process, right?
Yeah, it's a
The
mechanical
pumping.
process, but electricity is also involved, right? Because for doing the mechanical work, we need electrical input.
Of
That
course,
pumping
input. No,
pumping will
from
be done by electricity only.
But input is electrical, output is again mechanical.
The input is electrical.
Output is mechanical. Whereas in the discharging process, input is mechanical, output is electrical.
So but still we have to calculate.
Yeah.
Let us say this is not a pumped hydro storage. Assume that it's a battery. Then how will you calculate? Assume that the battery is the power capacity of battery is 80 megawatt, and for charging it takes 90 megawatts. Okay.
Yeah.
For charging it is taking 5 hours, but it discharges in 4 hours itself.
4 hours. Yeah.
So what
80
will be
megawatts.
the charging efficiency in that case?
80 megawatts battery.
80 megawatts, 80.
Yeah.
Yeah, 80 megawatt battery is there.
Is it there?
Yeah. Grid scale batteries are there, right? We have these, they are modular batteries. One module is of, I think 20 megawatt or so. No, sorry, not 25 megawatts. Now they have reached up to 5 megawatts. One module, one It is in the form of you have seen that for transporting that in shipping industry they have these big containers, right? What do they call it? Container? Is it called container or
Yeah.
container? So these batteries, also grid scale batteries, they are one module is in the form of a container. And one container, the rating of one container is around 5 megawatt.
Okay.
And such modules are connected in series parallel to give 1 gigawatt. Now we have very huge batteries. In Australia, I think the biggest battery is around 640 megawatt or so.
Oh.
Now we have gigawatt scale batteries also. That is not a single unit. They are made up of multiple series parallel units.
Yeah.
So yeah, 80 megawatt is possible.
Okay. So how do you calculate the charging efficiency?
So any just try to think. Any guess? What do you say? What do you think should be our approach? See, in charging, there is a loss, right?
Yeah, in charging and discharging, there is a loss of 10 megawatts.
Both way there is a loss.
Yeah.
In charging, the loss is there. That means we need more energy.
Yeah.
To charge it to its rated power. So this is the rated power, right? We want to achieve this, but to achieve this, how much do we require? To get an output of 80 megawatt, what is the input? Input is 90 megawatts, right?
Input.
This is the input only. We need to provide this much. For actual input energy, we'll say this is the input energy. 90 into 5. 450 megawatt hour of energy you need to. That energy, input energy is required to charge the battery to 80 megawatt.
Okay. So that means the round trip efficiency, you're taking energy efficiency, whereas for charging, you're taking only power efficiency.
So we can calculate. That was one way to calculate.
Okay.
But there is another way also. Can calculate the round trip efficiency. Just take the product of these. So how do we calculate the product? You can see. So this is the first one.
See, charging means from say down the reservoir to the reservoir.
Yes.
That means the process. So you are giving input at the lower side of the reservoir,
Yes.
and you are getting output on the other side of the reservoir, on the top of the reservoir.
Yes.
But you are taking, say, when you are using this formula 80 by 90, this 80 megawatt is measured at the lower end output. At the end of the process, you are getting 80.
Oh, this is the installed capacity of the. This is what the energy storage is supposed to deliver.
Okay,
This
that means
is the rating of the storage capacity. We want to charge the storage to its rated value. But for that, I need to provide more energy than its rating. So that means there is a loss. To charge it to 80 megawatts, I need to supply 90 megawatts. So there is a loss of 10 megawatts. So you can say, I am supplying an energy of 450 megawatts.
Yeah.
Okay, this is the input. But actual energy which I am getting, which is stored,
Okay.
is 80 into 5.
80 into
100 megawatt hour is not 100.
400.
50 megawatt hour is lost. Actually,
I
this
have a doubt here. I have a doubt. See,
this is the energy stored in the battery.
okay.
But when it discharges, we are able to get only 320 megawatt. Input was this, stored was this, but output is even lesser. So these are the three stages. This is the first. This is the input energy.
How you got the amount of energy stored in the reservoir?
Yeah, because you are charging the, you're taking 5 hours, right, to charge.
Okay.
This was the input. You are,
Of course, that is clear. 90 into 5, 450 megawatts.
yeah,
That is the input given to the process, entire process. Okay.
we know the rated capacity is 80 megawatt only. It cannot store more than that.
So means while discharging, there is no loss.
Yeah, it is there, right? From 4, stored energy was 400 and output is 320. So there is a loss of 80 megawatt hour.
Once
This
it
is
is
the loss.
stored, where this time is involved.
No, because once it is stored, it is discharging, right? It is discharging for 4 hours. In 4 hours,
Of
it is
course,
able to discharge completely.
of course. But say to calculate the amount of energy that can be stored, how can we use this five hours? Because you can do it at any point of time. Once it is stored, at any point of time you can discharge it. Even after 10 hours also you can discharge it.
Yeah, discharge, that can be done. Means when it is discharging, that is not the issue. How much time it takes to discharge or how much time it takes to charge, that will determine the stored or energy.
So,
Time taken to charge and
so
time taken to discharge.
for storing, you are using the time taken to charge.
Yes.
I have a doubt here, particularly so you are calculating charging efficiency, discharging efficiency. Suppose I have charged a reservoir for say 5 hours, let us say. I have not yet discharged.
Okay.
Water is there in the reservoir.
Yes.
How can I calculate the charging efficiency?
You have charged it.
I have charged it, not discharged it.
Okay.
How can I calculate the charging efficiency? Is there any charging efficiency for it or not?
You have charged it for 5 hours.
The same question. So 90 megawatts, 5 hours,
Okay.
but it is not discharged.
And that so it will be same, right? Efficiency will be same. It will be 400 by 450.
400 by
8/9. So let us make it more easier. This is the storage, right? Okay.
yeah.
This is energy storage, any kind of storage. It has some power capacity and some energy capacity.
Okay.
We are charging here. For that, some energy is required, which is input energy.
Okay.
These are rated values. Okay, so this input energy will always be greater than the rated because there are losses here.
Okay.
So charging efficiency will come into picture here.
Okay.
Now this storage wants to discharge. Okay, this is output energy.
Okay.
And this output energy will be always less than the
Input.
rated energy because there are losses here.
Losses here. Okay.
So what I'm saying here is, so this clear?
Yeah. Yeah.
So in our case, what is happening? The output energy is because 80 into 4.
Okay.
Okay, so this is 320 megawatt hour.
Okay. Input is also clear. 90 into 5.
Yeah, input is 90 into 5. It is 450 megawatt hour. Okay. And this stored energy is, we have used this input 450 megawatt was the input, megawatt hour is the input, but it is only charged up to 80 megawatts because its rated capacity is only 80 megawatts.
80.
So 80 into 5.
Regarding that, the 5 only. Say, for example, suppose if the same input was given, something like say 45 megawatt for 10 hours.
45 megawatts for 10 hour. Okay.
10 hours. So that means the storage is going to change now.
No, rated
80,
capacity will not change, right? It will never change.
rated capacity never changed. So now it is 80 into 10.
No, it is not 80 into change. 10, sorry. Because you convert this figure into 5. Make it 5.
How? Because the
Because,
time duration is 10 hours.
say, no, so point is, let's say, uh, have you heard of this C rating? C rating of a battery?
Yeah.
If C rating, right? If it is 1 C, that means in 1 hour it will discharge completely or charge completely.
Okay.
If it is 10 C, that means it will only take 6 hours. Sorry, 6 minutes.
Okay.
These are charging or discharging rate.
Okay.
Only the time to charge or discharge is changing, but the rated capacity, it will not change.
Of course, 80. In this case, 80 will not change.
80 will not change. So what you can do here is, in that case, this is 45 into 10, right?
Yeah.
So you make it you have to make it 80.
So charging is little bit slow, but overall energy is same.
Yeah, energy will same. Yes, energy which is stored will
Yeah.
remain same.
So stored is okay, same. 80
Yes.
megawatt is the rated capacity of the storage.
Yes.
But you are using that charging time in calculating the energy stored in the reservoir.
So this is uh, just to explain. Actually, it, it will change also.
Okay.
It's just to explain
Okay.
that if it just to explain that if input is this much, there is some loss.
Yeah.
It is only from 90 to, although we are giving an input of 90 megawatts for 5 hours, it is only charged to 80 megawatts.
Yeah.
So I am saying that if we are charging it for 5 hours and 80 is the 90 is more than its rated capacity, then it will be only charged up to 80.
Okay.
So for 5 hours, it will store only 18 to 5.
Okay.
Right? And if I want now, rated capacity is 80 and I want to discharge it at its maximum capacity, 80 megawatt only,
Okay.
continuously.
Continuously.
So
Okay.
I want to see in how much time it will discharge completely if I discharge it at maximum capacity.
Okay.
So it will discharge in 4 hours itself.
Yeah.
Although it took 5 hours to charge to at the same rate, 80
Mm-hmm.
megawatt per hour, but while discharging at the same rate, it discharges in a lesser time.
Okay.
Is it clear?
Yeah. Yeah. Yeah.
So here assumption in this calculation is the charging rate and discharging rate are same, which is 80 megawatt per hour. Per hour. If it charges at 80 megawatt per hour, then energy stored is 400, right? Because we are charging for 5 hours only.
Yeah.
And it is charging at 80 megawatt only. So 10 megawatt, there is a loss per
Yeah.
hour. And if it discharges at same rate, then there is a loss of total loss of 80 megawatt hour or 20 megawatt hour per 20 megawatt per hour. There is a
Per
loss.
hour. Yeah.
Is it clear now?
Yes. Yes. Yes.
So now what will be the charging efficiency now?
I think it's 80 by 90 means.
Yeah, so it is 80 by 90.
88.88%.
Yeah, and what is discharging efficiency?
Charging. It's around 80%.
How did you calculate?
No. Using this formula. At
Which
the
no, don't use that. Means directly you have to calculate. Means we are calculating RT by product of these two. So
yeah,
first you have to calculate this discharging
discharge
efficiency.
discharge
Yes.
efficiency.
So how will you calculate? You can use this, right? These two values.
Yeah.
So what will be
100
the
T20.
efficiency? How will you calculate?
T20 by 400.
Yes, so you can say 4 by 5.
Yeah. 80%.
Now this will be product of these two, 8 by 9 into 4 by 5. Okay,
Yes. Yes.
so you will get 71 point.
100.
Is this clear?
Yes, sir. Yes, sir.
Good question.
Yeah.
Okay. Okay. Yeah, the width was. We have discussed this one, right? Sixth.
Yes.
Let us move to 7th.
E
Two
into B.
generators, A and B, have speed regulation of 5%. Same group. Rating
Same
is
group
200.
means proportionate to the capacities.
Yes, correct.
2:3 ratio.
Yeah, so rated at 200 and 300 megawatt. Total load is 400 megawatt.
So
we need to find out
proportionality
PA
they are
by
rating, they will share the load.
yeah, provided they have same no load frequency.
Yeah.
This will work only when this assumption is there.
Yeah, with same load frequency.
Otherwise, it will change.
Yes, yes, yes.
So what is the answer here? It's very easy.
2 by,
Right?
2 by 3.
2 by 3. So see here. This is the way you can calculate it.
Yeah.
If this we were able to do directly, we were able to do it 200 by 300 proportionate sharing, because F naught A is equals to F naught B, or the no load frequencies are same. If it is same, then this cancels out. And because droops are also same, this also cancels out. We are left with only this PA by PB is equals to 2 by 3, right?
2 by 3.
But if it is not same, then we cannot do this.
Yeah, we have to give some other data
Then you
also.
will get this.
Yeah, yeah.
If they have same droop, then you need to know this. What
Yeah,
is the initial frequency, no load frequency, or speed of these two generators?
Yes.
So this is required in that case. So it will be 1.5 into this no load frequency.
Yeah.
So this will be required. So here both are same, so it becomes 1.5, or PA by PB becomes 2 by 3. This is 3 by 2. Yeah, clear?
Yes, sir.
Yeah, then this is, I think, next question is also continuation of this only. Here we have considered that the droop is same,
Same question.
5%, right? Next
Yeah.
question is the droop of generator A is 4% and droop of generator B is 5%. Then
We
what
will
is
use the
the,
same equation.
yeah, we'll use the same equation, but what will change?
Where is the question, sir?
Okay, let me show the question. Yeah, this is the question.
Yeah, yeah.
I think here load is also changed, right?
Load.
Load here load was 400, now load is 500.
500 megawatt.
But we don't need that.
Load, I think, no, we require load also.
If
It's
this
50.
no load frequency is
What is
same,
the
then if no load frequency is
frequency?
same, then we don't need it. Because when you take ratio, they will cancel out.
Yeah, yeah, yeah.
You can directly calculate without this information. So this, if we are given with this information, then we need the third equation, PA plus PB is equals to 500. If it is same, then it is not required.
PA by PB.
But PA plus PB equation is required to calculate PA and PB. Without this equation, we can only know the ratio. If load is not given, then we can only calculate the ratio. We cannot calculate the individual values if this is not given. Okay?
Yes, sir. Yes, sir.
Yeah, so now calculate, here we have this 4% droop for generator A, 5% for droop
5,000 by 22.
B. We have to calculate the ratio here. I think these options are incorrect. These options are not correct.
X value is 227 means PA.
Okay.
Minus 500. It's around 272. So 227 by 227 by 272. So 0.834.
I don't know the answer. Let's just check. But we don't need to, without calculating P and PB also we can do it. So you can directly do this, right?
Hmm.
Same equation. These no load frequency is same.
Yeah.
So this also
The
cancels
change in
out.
frequency is same. Yeah.
Only these droops are different. That is why this factor of 5/4 comes into picture.
Yeah.
So it becomes 2/3, which was already there, multiplied by 5/4. Earlier it was 5/5. So it was
Yeah.
simply 2/3. Now it is 5/4
5/4.
into 5/4. So 10 divided by 12 or 5/6. Okay.
5/6.
So whenever you
Yeah,
are
same value. 0.83.
so whenever ratio is required, no
Yeah.
need to calculate A and B. Just write the equation, divide them.
Yeah.
Directly you can calculate the ratios.
Yes. Yes.
Unless both are individually required, no need to calculate. Just
Yeah.
divide the two equations and you'll get the ratio.
You can. Yeah, because the change is PA and change in generator is PB. So PA plus PB is the total demand. Okay.
Yes, correct.
Okay.
Yeah, I think this is the last question.
Uh,
Frequency sensitive load connected to 60 Hz system changes by 1.25% for a 1% change in frequency on 500 kVA system base. If the system base is changed to 1 MVA, what is the value of D in per unit megawatt per hertz?
D value means it's per unit megawatt by hertz. Okay. Per unit megawatt.
Because this is delta P is equals to D into delta omega, right?
Yeah.
The units of D will be change in power divided by,
Change in power by change in
yeah, so
frequency.
that is
Opposite to
megawatts.
R.
Yes,
Opposite to
opposite
regulation.
to R, correct. It is megawatts per hertz only.
Yeah.
We are calculating it in per unit.
1 point frequency into load connected to
This is in,
change in load is 1.25.
yes, 1.25.
Mm,
And change in frequency is 1%.
1.25. This is percentage.
Yes, so first, because we want it in megawatts per hertz, first we need to convert this change in frequency into hertz, percentage into hertz, right?
Yeah. Per unit megawatt per hertz. Per unit megawatt. Okay.
So here the change in system base. First, you can calculate it on the machine base, which is 500 kVA.
100 kVA.
No, sorry. Yeah,
Fine,
first you have to
kVA.
calculate
This is
it
MVA.
on first base, then convert it into 1 MVA base.
1 MVA base. Yeah. It's 0.5. 0.625.
0.625. How did you calculate?
No. I think this frequency is in hertz, so that is to be changed, I think.
Also, you need to convert. So this is megawatt per hertz. You need to convert this into megawatts.
No, that's per unit, right?
This into hertz.
Per unit megawatt per hertz. Power is in per unit megawatt. Power value is in per unit.
Yes. Yes. So this will be D, right?
Yeah.
In per unit megawatt hertz. Correct?
Yes.
So how much is this?
1.25 by 60.
So this will be 0.02083.
0.083.
So this is on 500 kVA system base.
Okay.
Now you need to convert this into 1 MVA base, system base. Now a
It is
new
multiplied by 2.
multiplied by 2. Why?
500 kVA. MVA means 1000 kVA, right?
Yeah.
So to convert that, you need to divide with 500 and multiply with 1000.
Yes, correct. No, not correct.
This per unit megawatt, this is the numerator.
So see, this is
Oh, no, no. So that is per unit megawatt. So you need to multiply with 500 and divide with 1000.
yes, correct. So you need
By
to
2.
multiply this by by 2. Divide by 1. So by 2.
Yeah.
So it will be 0.01046.
Yeah.
So this will be the correct value.
01046. I think none is the answer.
Yeah, none is the answer. Okay.
Yeah.
Yeah. So all these are the questions for today. So any other doubt?
No, sir.
Okay, then we'll meet next Tuesday.
Yeah. Last.
Thank. Was
Okay.
it
Okay.
helpful?
Yes, sir. Yes, sir. Very much.
Okay, I will upload this PPT on the portal. You can
Okay.
see, have a look at it. Thank you for joining.
Okay. Okay. Thank you. Thank you.
Bye.